port numbers. Now, what happens when we have this? We're going to assume, and think about this, when we have a standard transmission line, just a regular transmission line with a load. I'm just going to put a load here, ZL. If I have this, we know that on this transmission line, we can have a plus or minus voltage where the wave would be in the plus direction propagating this way. I can also have, superimposed on this, I can have a wave propagating in the negative direction. That wave would be designated minus S. In other words, we're going to decompose the total voltage on a transmission line into a voltage that's going in the plus direction and a voltage reflecting going in the minus direction. Now, this is simply a one-port network, in other words. There's only one set of terminals where voltages can be developed. But there's going to be something where it's propagating into it and then reflecting from it. Does that make sense? By the way, how many people remember what the criteria is as far as the length D of this line before we start considering this an actual transmission line, and not just a couple pieces of wire? How many remember that? Tenth of a wavelength. This thing has to be, D has to be greater than approximately 1/10 lambda. Now, transmission lines operate at high frequency, and that is one of the things we assume. This S parameter network, however, doesn't have to be that big. It can be very, very small. But these transmission lines, in order to behave as transmission lines, need this criteria, or they just look like a couple of straight pieces of wire. Now, when we have this, what we normally say, as at on the first port, you have two waves developing potential plus to minus. You're going to have a wave V plus that's propagating in this direction. Just write this down. I'll get rid of the abstractions in a second. And you're going to have V minus propagating in this direction. That would be on port 1. So the way we designate it, by the way, can you see this in the far back of the room? I'm going to designate this V1 because it's in port 1. The plus sign indicates it's a voltage going in or propagating into the actual box. Now, probably an obvious question is, what's in the box? Anything could be in the box. It could be resistors, inductors, transistors, anything. We look at it as a black box simply because we don't want to in any way constrain ourselves. With one exception, I'm going to say, generally, we try to look at linear systems. Not always, but generally linear systems. Because if they're nonlinear, some of this stuff gets really hairy. So now we have two waves coming in to port 1. In port 2, this is port 2, we're going to have a wave going into it. Remember, when it's going in, it's going to be positive. V2 plus, anything leaving the port will be negative. So I'm going to have a wave here that's V2 minus. That doesn't mean a lot to you yet, but at least you're starting to see we're setting up some sort of method of discussing what's going on. Now we need a relationship between these two. It doesn't matter what's inside here. We can measure the relationship between these parameters, and that's what are called the S parameters. So inside here, there are S parameters. And they're usually measured in the real world. I've done quite a bit of work on this. Those are measured parameters. Now, what are the relationships? And by the way, S parameters are just one set of parameters. If you take microwave from Dr. Whitworth, you're going to see there's a whole bunch of them. There's S parameters, A, B, C, D parameters, H parameters. Didn't you have H parameters when you had analog? Most of you? There's all sorts of ways of designating a two-port system. Two-port means you have a differential voltage on the input, or you have a plus-minus voltage on the input that defines some input conduit, and a plus-minus voltage on the output that defines an output conduit. But they aren't single lines referencing the voltage of each other. They were always with respect to a ground voltage. So keep that in mind, usually. when we have this, the relationship between the voltages is V1 minus is equal to S11 times V1 plus S12 times V2 plus. Now that's the relationship. It doesn't mean a lot to you yet, but it will in a second. V2 minus is equal to S21 V1 plus S22 times V2 plus. I'll get, in a second, I'm going to get to what each one of these mean and why they mean it, all right? Now, we never write stuff just like this. We're engineers. We write them in a matrix. So generally, we put V1, V2, or excuse me, is equal to S11, S22, S21, S12 times V1 plus V2 plus. This is the way we designate that in a matrix form. And what you're going to see in the book, please write this down. You won't see it always separated like this. You will see simply a bold S in here. You'll see a big S like this that designates the actual parameters inside here. They'll just have a big S. But it's understood that it's a matrix. That's important. Now we take a look at this. And I'm going to be talking about what actually happens here. Now, I'll tell you what, I'm going to use this figure and just pay attention to this so I'm going to make some points and then I'm going to write it down. If we look at the first equation right here, for a second, I'm going to write it over here. I'm going to take V1 minus is equal to S11 V1 plus S12 V2 plus. Now think about what's going on here before I continue. We're assuming we have some signal incident, some V1 plus here, don't we, class? I mean, that's what that is. It means it's a signal propagating in this direction. With me? Now there's also going to be a V2 plus. V2 plus is something that indicates there's some V2 plus or some other stuff is out here where a wave is propagating into that core. Well, that's pretty complicated. That doesn't tell us a lot. So what we like to do, because we like to get these things down to physical things that we're used to seeing, something we understand. If I have V1 minus is equal to S11 times V1 plus, but I assume that this term isn't there. So I'm going to say plus 0. That means, in order for that to be the case, V2 plus has to be 0. In other words, I'm going to make sure that nothing's propagating in from this thing, correct? And the only way I can do that is make sure this has a characteristic impedance of Z0, that the load here has a characteristic impedance of Z0. Because that way everything that goes through there wouldn't reflect that. Does that make sense to everybody? I'm going to see this right here. All right. You good with that? There's nothing reflected back from this point if this and this are matched, or if it's a matched condition. Now, what does that actually mean? Look at this for a second, I know you know it. If I take V1 minus over V1 plus equal to S11, don't answer yet, think about this. That's a ratio of how much of the wave is reflected compared to what went into that point, right? What did we normally call that when we had a transmission line like this? And we wanted the ratio of V plus, or excuse me, V minus over V plus. Remember that? What did we call that? Not the first couple of rows, in the back. Do you remember that? What's the ratio of something that gets reflected? What is that called? Reflection coefficient. How many remember that? This is the definition of the reflection coefficient, right? That would be, now think about it, that works for electric fields as well for voltages, right? The reflection coefficient is, by definition, it is the ratio of the reflected to the incident wave's magnitude. And we can talk about other things. There are phases, but it's really, it's the ratio of the two waveforms. Now, what does that really mean? When I effectively match this part of the circuit, or make sure there's no waves that can go through here that can get out and reflect back, the only thing I'm looking at is the reflection coefficient here, right? Now think about this logically. What is the reflection coefficient? If we're talking about impedances here, well, if this line had a characteristic impedance of Z0, could you assume there was some Zn looking in there, class? How many see that? You could assume there's an input impedance. Do you agree, class? Well, what would the reflection coefficient be if I had Zn? Suppose I knew what Zn is looking in there. I'll give you a concrete example in a second. But if I knew what Zn was, and this was Z0, what would the reflection coefficient be? What do we do when we want the reflection coefficient? If we just had this right here, Z load, and this was a characteristic impedance of Z0. How do we get the reflection coefficient, or better, yeah, why don't we get the reflection coefficient right here for this one? What do we do? Can you see it in the back? Can you read that ZL? What do we always do if we want reflection coefficient, class? Don't we always look at the impedance we're going into, ZL, subtract from it the impedance where we came from, Z0, divided by ZL plus Z0. Does everybody recall that? Now here we don't have ZL. We have some Zn that we don't know yet. But when I start putting circuit elements in there, it'll make sense. If I put a parallel resistance here, and a series resistance here, and I say this is 50 ohms, I guarantee you can figure out what that value is. But for now, I want to make sure you understand why we're doing this. That's the reflection coefficient. That's something that's measurable. The next term is S12. I'm going to write it over here. I'm going to still use that drawing. Make sure everybody understands this. Now we have V1 minus is equal to S11 V1 plus S12 V2 plus. Now I draw my thing here. Here's port 1, here's port 2. I'm going to assume, now I want to figure out what this means here. And this is something that all of you that have analog know instinctively what it is. Because there was one single thing that you thought about all the time that involved this. But at least you did once you analyzed it. Once you had the circuit mathematically illustrated, you did it. If I take a look at this, what I really want right here is to get rid of this term, V1 plus, right? Now think about it, don't I? I say that, and now I'm almost questioning myself, because I'm not sure in analog if they did much with any of this. Didn't you get forward gain AB, forward voltage gain, and reverse voltage gain for your transistor class? Do you remember the forward voltage gain is? You put an input voltage like a millivolt. It was a gain of 100, you got 100 millivolts. You remember that? Well, this is like a reverse voltage gain. You're going to see it in a second. Here, I know V1 minus is in this direction. Right? I know V2 plus would be in this direction. And of course, these are differential voltages. They won't keep on putting this plus minus here. They assume you know that the voltages are developed across these 2 points. Everybody all right with that, class? Now, if we take a look at this, if I want to just get the ratio of V1 minus to V2 plus, I can get S12, right? That means I have to make sure there's no signals or that V1 plus is equal to 0. In other words, I could not be transmitting in this direction. But I sure could put a matched load here I could put some Z naught here and Z naught here, and I could say that V1 minus would be equal to, I'm going to zero that term out because there's going to be no waves transmitted this way, no V1 plus. You all right with that? Can you see it? I'm going to get rid of that, and I'm going to say it's equal to S12 times V2 plus. Now, what is this really? I've got a ratio of how much is coming out of port 1 to what's going into port 2, don't I? So now I can say that V1 minus over V2 plus would be equal to S12. Anytime you have a ratio of a voltage going out of something compared to a ratio of what went into something, isn't that a voltage gain, class? How many remember that? It's a voltage gain. This is the reverse voltage gain right here. You can write it down. I don't think he puts it in the book, but this is the reverse voltage gain. Really, it's not even a gain in the true sense. It's usually a loss. But it's simply depicting the ratio of the input to the output voltage. And you know, you're engineers, that's almost automatic to you because you're used to doing voltage division, aren't you? That's all this is, voltage division. If you don't have active elements, if you have a transistor in there, then it's different. But so far, this is straightforward. Now, think about this before I'm going to put the next part up. Now suppose I don't even have my S parameters here, maybe I should put them over here. I know I have V1 minus V2 minus is equal to S11, S12, S21, S22 times simply V1 plus, V2 plus. You know that. I'm going to work on the next one down. I'm going to say V2 minus is equal to S21 times V1 plus S22 times V2 plus. And now we're going to take a look at what each one of these things signifies. I bet you'll see it. If I do this, and I take the ratio, first suppose I want to make sure, now here we're going to assume that V2 plus is equal to 0. Make sure you understand what that means. There's no incoming wave, right? If V2 plus is 0, what am I actually getting when I get the ratio here of V2 minus over V1 plus? That's S21, isn't it? Now I want you to think about it for a second. What does that mean? What am I actually doing? I'm getting the ratio, and I'll draw it right under here. If I have this circuit, this is port 1, this is port 2, I have V1 plus, so here I have V1 plus, and I'm getting out V2 minus, right? If this is port 1 and that's port 2, what would you term that? That's how much I'm getting out of the network, right? I'm putting in, and this is in the forward direction, not in the reverse direction. I'm putting in some voltage. It could be 1 volt. If it's a voltage gain, it would be greater than 1. I could get out more than 1, right? Usually that entails an active network transistor. Or I could get out a lot less, but that's really, this is a voltage gain here. This is a forward voltage gain. Forward voltage gain. Honestly, these things are so easy, but a lot of times if you just read about them, if you got to learn this stuff on the fly, you're wondering what in the world's going on. It's not hard. As long as you understand what the concept, why they're doing this. They're taking a look at reflection coefficients of the two-part, and they call them transmission coefficients. I think you're more familiar with voltage gain myself. But transmission coefficients are fine as well. So now I have this. Any takers on how to get S22 and what it means? Anybody? What do you think S22 is, based on what S1 said? Think about what the ratio would be. If I wanted S22, what would I have to do? I would want to set V1 plus equal to 0, wouldn't I? Follow me on this. If I do this, then if I take a look at this, now I have S22, if this is equal to 0, is really equal to V2 minus over V2 plus. Now, think about that logically. You got a wave coming in, it's got a value of V2 plus, something's reflected back from the same port, V2 minus. What might you call that? What did you say?
Reverse.
What could be, sure, it's a reflection coefficient of port 2, or a reverse reflection coefficient. You could call it that, I guess. It's a reflection coefficient. This is simply the reflection coefficient on port 2. That's it. There's no magic on any of it. Now, I had to get through this today. Next class period, I'm going to start on this stuff. I'm going to give you some simple stuff here. I didn't get a chance to do an example. If you have questions about the test, please see me. I'll get those solutions up on the internet. Redo some of this stuff on Dropbox.